Hey everyone, and welcome to today's Explainer. We've got something really special for you today. We're pulling from some fantastic Bengali source material, which means our entire focus is on a concept known as Bakada. Basically, that's the art of pure, deep, and beautifully structured explanation. We're going to use that approach to break down one of the most fascinating and totally invisible forces in the physical world: static electricity and electrostatic induction. We'll take you on a journey, starting right from a wild physical process all the way down to a side-by-side comparison of the hidden forces making it happen. So, if you love figuring out exactly how the world works behind the scenes, you are absolutely in the right place.
So let's dive right into this with a question that honestly sounds a little impossible at first. How do you charge an object without ever actually touching it? I mean, we're so used to physical changes requiring physical contact, right? But out there in the quantum realm of electrons, influence can happen entirely at a distance. What we're really unpacking today is the crazy mystery between a temporary physical state and a permanent one, and how an invisible field can essentially just manipulate matter.
All right, let's get into Section 1, Polarization.
Okay, picture this. Imagine bringing a highly charged foreign object right up close to a totally neutral conductor. They aren't touching at all, but the mere presence of this new object literally changes everything. It creates this massive, dramatic split. Polarization is exactly this process. It's where the near end of a neutral conductor suddenly becomes negatively charged and the far end becomes positively charged. And why does this happen? Well, it's all about a super rapid movement of electrons. That charged object you brought in close, it acts like a giant magnet for electrons. Say it's a positive object, the electrons in the neutral conductor just brush toward it, creating a huge pileup of negative charge at the near end. And because those electrons completely abandon the far end of the conductor, that far end is now left with an electron deficit. That makes it completely positive. It is a rapid, instantaneous, internal migration of energy, and it's so cool to think about.
So, let's look at the exact anatomy of this conductor now. You've got negative at the near end and positive at the far end. The really important thing to remember here is that the neutral object hasn't actually gained or lost any total electrons from the outside world. Not a single one. They've just severely reorganized themselves. One side is incredibly crowded, almost like a traffic jam, and the other is completely deserted. It's an incredible state of internal tension, and it's driven entirely by that outside non-touching influence hovering just millimeters away.
Moving right along, let's hit Section 2, a temporary state.
Now, here is the great narrative twist of electrostatic induction. That massive reorganization, that super impressive polarization effect we just walked through, it's actually just a fleeting illusion. Our source material puts it perfectly and plainly. The object simply becomes neutral again. So what causes this sudden disappearance? Well, it all comes down to the source. If you take that original inducing charge, that foreign object you brought close, and you just move it away, poof, the spell is broken. Without that external magnetic-like influence holding the electrons hostage at one end, they instantly repel each other, spread back out evenly across the conductor, and reset the whole system. In a fraction of a second, your highly polarized object is just a standard, boring, neutral piece of metal once more.
Which brings us to a really fascinating dual reality in Section 3, inducing versus induced charge. We really need to slow down for a second here and analyze these two very distinct characters in our physics play. Understanding the difference between them is absolutely crucial. It's the key to mastering this entire concept. First up, let's look at the inducing charge. Think of this as our visitor. It's brought from the outside, and the total amount of its charge absolutely does not change during this whole process. It is the steady, unchanging instigator. Now contrast that with the induced charge. This is the reaction. It is the newly created, localized charge that split inside our previously neutral conductor. And as we just learned, its existence is incredibly fragile. It vanishes completely, practically disappearing into thin air the very moment the source is removed. So one is independent and unchanging, while the other is completely dependent and totally temporary. And looking at the exact source breakdown of electrostatic induction brilliantly illustrates where all this structured logic comes from. The original text elegantly maps out these precise mechanical states. It lays out the definitions of polarization, that fleeting temporary state, and the strict, hard boundary between the inducing catalyst and the induced reaction. But you know what makes this source material truly excellent? It doesn't just hand us the facts and call it a day. It realizes that just understanding this temporary state isn't quite enough to satisfy our curiosity. It intentionally sets up an even bigger question for the inquisitive mind.
Which leads us directly to this awesome final cliffhanger pulled right from the original text. Want to know how to charge an object permanently? Because think about it.
If pulling the source away resets everything, how do we trap those electrons and actually make the charge stick? Well, the source hints at a permanent solution called grounding, which essentially gives those fleeing electrons an escape route to the Earth, trapping the positive charge forever. Or hey, perhaps you're wondering how the math of all this actually calculates out. That is the true beauty of Deep Baja. Every great explanation just opens the door to the next incredible mystery. Until next time, keep questioning those invisible forces around you.